button. That button. And hopefully we come online. Hey Ravi! Hopefully I didn't get the time too wrong, and hopefully I think we've got radio parallax in the background at a decent audio level without too much hum. I'm just trying at the same time as well under Wine to install the actual Twitch desktop client. But so far, without luck. Well, it's running, but the display is all black, which is, shall we say, counterproductive. Hey Marauder, welcome along as well. So I think we'll just continue the way we've been doing it previously. So we are again looking at the floppy stuff. So let me just get the right Bitstream loaded on the MEGA65 here. It will be that one from earlier in the week. And welcome to everyone else who's hopped on. Feel free to say howdy and ask questions as we go along. So, as a brief bit of intro again for what we're trying to do here. So the MEGA65 has a built-in floppy drive, which you should now be able to see transparently. So we have the floppy drive. We have loaded in the floppy drive a standard 1.44 meg floppy disk. Should you know that? Is that the one? Maybe it's the one I was using before. That's fine. And we are trying to get the maximum capacity out of that we can with the MEGA65, because we know that 1.44 meg floppies are well off what's possible to put on the disk, if only because the outside tracks are a lot longer than the inside tracks, and therefore the data rate by default is set to that which the inside tracks can handle. Hey Andy Magic Knight. Where was I up to last time? So that's right, I was trying to get RLL encoding working. So I've done some work on the RLL encoding side of things, and so I can show you. Let me just make sure that yes, it's E for encoding. Right, okay. So we can do the view histogram. Right, so this is RLL encoding at the standard double density disk, so 720k disk density. So we've got the three peaks happening there. They're quite widely spaced. We currently have no write precompensation enabled, although it's less needed at this low kind of data rate. Hey LGB. LGB says, I could catch the stream here in the countryside as well. Not the best internet connection, but here anyway. Welcome along. And so we can, if I use O and P on the keyboard, this will change the timing, so we can speed it up by reducing the divisor. And what you see up here, so the data rate being 43 hex, that's the current divisor. And the TIB is showing what's being read back from the track information block. And up here we have the sectors that are being read back. So it's giving us an idea of how many sectors we can fit at that data rate. And so we'll get more sectors as we increase the data rate by reducing the divisor down. Andy Magic says, I'm staying authentic. I'm using 1980s internet, i.e. watching from floppies. Excellent. So we can keep winding that back. So a data rate of $2.28, so a divisor of 40, i.e. 40.5 megahertz divided by 40 gets 1 megabit of MFM transition. So this is the key thing. The actual data rate will be half that. So as we come down, we will see it's interesting. The peaks get a little bit narrower as we kind of get to a bit of a sweet spot around that. I presume because the drive electronics are a little bit optimized for this. But we'll also see is that the middle peak is fatter than the other two, presumably due to horrible magnetic effects and things. So that's now at the 1.44 meg floppy rate, and we can bring that back. And what we need to do is to keep those peaks separate. So that's probably about as far as we can get there. And we start to see that the peaks are breaking up at the top. So if I start adding some write pre-compensation on. Now I did find a floppy drive manual during the week that actually said that the ideal write pre-comp for a floppy drive should be 125 nanoseconds. So that's 5. Hey, line 23. So we can enable that, and then we also separately, again, this is just doing a bit of a quick recap for everyone. We can move this middle peak to the right so it's better separated between the other two by using some other write pre-compensation magic that I worked out. You can see it will be slightly moving across to the right. So that's about centered. And so now we can try to further reduce the data rate. And we see that it does break down at some point. The other thing, if you're watching carefully, you'll notice that there's occasionally there's a little bit that shows up out here to the right, these little tiny peaks. And you'll notice that they actually correspond to the double data, the normal 720k density. That's the track information block that's always encoded at that rate. Andy Magic Knight says, tangent quest, but A, is that currently reading from a physical 3.5 inch floppy disk? And B, does the MEGA65 have a floppy light, or is that green light the floppy? Yes, so that's from a real disk. So you see now that the histogram is frozen because it's not getting any more pulses. And that green light there is the floppy disk light. So if we were to turn the motor off, I have to remember now, I think, there you go, floppy motor is off, floppy motor is on. You're welcome. So, that's about as far as we can get with MFM. Hey Prowl7, welcome along. So what we want to do is to switch to an RLL code, in the first instance an RLL 2,7 code, because the minimum gap between the pulses is longer. So this is a histogram, right? So it's saying that the first cluster of pulses is about, from the left edge of the screen to there long. The middle sized pulses are a bit longer, and the longest pulses are a bit longer again. So just bear in mind that there's always at least this much gap, but what we see with the floppy electronics is that it can't resolve peaks that are much closer than that without having big problems. And you can actually see still that there's a double peak still here on the smallest one, so there's probably still some further magic that we can do with the right pre-compensation, but it's quite bizarre. We should try. I'm wondering whether if I shift that the other way, that moves, even though it splits the middle peak, whether it moves the other one in, but it doesn't. So there's some other corrective measure that would be good. So what I then implemented during the week, if I press the E key, this will switch our encoding from MFM to RLL 2,7. So this is what the early PC hard drives used. Now I've left the data rate the same, so you see the first peak, is further to the right. So it's all the peaks, the magnetic flux transitions are further apart. So the drive is much, much happier about this. And we haven't changed the data rate. So we can see that with the RLL encoding, we're actually going to have better performance, and it means that we can wind the divisor down a bit more and still resolve them. So I think 1.7 is probably too low. 1.8 or possibly 1.9. Like 1.9 is definitely fine. And again, if we were to switch back to MFM, we'd see that we just have an utter mess. So the RLL encoding is definitely helping us. So the important thing to bear in mind, remember that this data rate is a divisor. So on MFM, what did we say? It was about 1E was the best that we could get. And we can certainly get 1.9 instead with RLL. And again, we see that we have this effect where the this second peak shifts to the left. I'm sure there's a very fascinating magnetic physics reason for that. I don't know what it is, but it suggests to me that we could use the same right pre-comp trick that we did in MFM. The other thing to bear in mind is that the right pre-compensation values are ignored at the moment with RLL. There is no right pre-compensation. So we're at a disadvantage compared to MFM in terms of squeezing every last bit of performance out. So one of the things that we might do this morning is we might try and add in that right pre-compensation for RLL. And that should let us, if you have a look at the thing, if we come down like to 1.7, there's probably enough space to resolve. 1.6 I think is not going to work, but 1.7, yeah, probably. 1.8, certainly we should be able to move that peak a little bit. 1.9, which we can already do, is pretty good. So the other thing that we might try and look and figure out what's going on today is that the we should be seeing up here all of these sectors getting picked up that are on this track, and for some reason it's not. So we might have to do a bit of a capture and fiddle with my tools to see if the sectors are somehow being written wrong with a wrong data CRC or something in RLL, whether I've messed something up, or rather, what have I messed up? But let's for a moment have a look at data rate 1.9 versus 1E and see what that means in terms of expected capacity. So 1E is 30, 1.9 is 25. So in very simple terms, we should get 1.2 times the number of sectors on each track. I know Anti-Magic is saying, does the floppy control code run from the hypervisor or as part of the MEGA65 OS? So it's from user land. So you don't need to be in the hypervisor to do this. It's literally just poking pokes from user land. So regular software can abuse the floppy controller as much as it wants. And that's pretty easy to do. So I think I will try to capture one of these tracks and see what we've got stuffed up. So if we do that, okay, we're in RLL encoding. We'll bring the data right back. We'll come back to track 0 as well. Okay, so now we can find the data rate back. It's interesting, you see this kind of, there's this noise when we have the data rate really low in RLL. And I think this is actually because we have some pulses so long, the floppy controller electronics actually gets confused and starts reading into the nothing. So in fact with RLL we have to have, there's a minimum data rate that we have to have for it to be reliable. And you'll see that basically disappears by the time that rightmost peak comes back to about where it was for a double density MFM encoding, because that's what the electronics is based around. Okay, so we've now got the track written nicely with RLL rate 19. And so before we were not looking at track 0. I'd forgotten this. So we can actually, I think 17, or certainly 18, but maybe 17 is doable. Let's try 17, and if we can decode that track, then that'll be great. So that will be even more on the track. So we need to go run stop, use option 5, read track 0 into memory, and then I've got to where's my screen gone? Oh, hang on, I need to plug the HDMI in so that we can get a display up for you guys. And we'll get that to a size that doesn't require glasses for anyone. Seems to find where my mouse cursor is gone. Monitor, save, address, track 0, we'll just call it RLL 0.dat. And what have I stuffed up there? Because it's talking on the wrong serial port. So when I have my laptop on the docking station, I have more USB serial ports. So it's line 3. Need to update the monitor save program. I haven't modified it for ages, so it doesn't have the improved auto detection of USB serial ports. Line 23, what do you use to get the MEGA65 screen into the stream? It's slightly complicated. The MEGA65 goes into an HDMI splitter. The splitter feeds the monitor to my right so that I can see the screen myself. And then the other output goes into a Kramer 457 VP728 upscaler, which the university AV people were going to throw out, so they gave to me instead. That upscales it to 1080 in a really nice way, and then that feeds into an ATEM Mini Pro that's actually doing the stream, and so that's how I can do the nice blendy effect with the camera, which I think works quite nicely. Okay, so now we have that data. Make bin MFM. It's still called MFM decode, even though it's not really only MFM. Yeah, Prowl 7. So the reason I'm going to throw it away is that those upscalers, if you leave them on 24/7, they eventually burn out their power supply. And they got sick of having to replace them. But because I only have it powered on when I'm streaming, it'll last for 1,000,000 years. But yeah, as an upscaler, they are fantastic because it's a 19-inch rack. mount full industrial kind of thing. So it's got funky controls on the front. I can freeze frame the MEGA65 with it, which we may do at some point for different things to be able to look at dynamic displays. And yeah, and so it looks nice. And yeah, and so the audio from the MEGA65 I think is passing through that whole chain as well. But anyway, let's see how I've got this set up at the moment. So this program produces somewhat confusing output, and it's probably also currently configured for some specific data rate and things. So we need to set the default rate. So ignore the fluff about, hang on, so we're using the other file format. Actually, what did it say about all of that? This is really a hacky tool that I've made, right? So assuming a D6A0 capture, which it probably is, so that 29 does need to get changed. So what we need to do with this is to modify it so that when it finds the track information block, it will switch to the encoding and data rate described in there. So I'm not convinced that that's in the right mode, because there's some other funky options for this thing somewhere. Pre-comp rules, gap quantize. Because we know that the track information block is good because we actually see the track information block being read, showing the data rate for it. So I'll show you what the capture format looks like here. So this is actually reading the raw floppy disk lines repeatedly. Bit 4 of the byte is the read data line. So here we can see it goes negative for a while and then goes positive again. So that's the floppy drive indicating a magnetic inversion. This is, at the end of the day, what the MEGA65 floppy controller has to work with. Hi, James Anderbanks. Welcome along. Yes, indeed, it does seem to know your name. So that all looks good. So 1.5, 2.0. So these floating point numbers that you see here are the quantized gap length, according to the MFM gap lengths. So a sync mark in MFM looks like 2.0, 1.5, 2.0, 1.5. So we should see such a thing at some point. We can actually see here. So here's one where it's detected one, but any of these kind of sector areas or the track information block have 3 sync marks in a row. This is how the floppy controller knows that it should be paying attention and start decoding something. So we're seeing the odd, well, there's 2 in a row there, but there's not 3 in a row. But there must be 3 in a row written to the disk because the track information block is getting decoded. So I'll search for 65. hex, because that's actually what's in the track information block marker. So it's possible that we're reading the wrong side of the disk. So I'm just going to switch back to here. I thought I had a command set up in this so that I can flip which side it's writing to. What have I got? I've got all sorts of commands in this mode. So plus and minus changes the track. Decrease rate. We don't want auto tune. HD disk, DD disk by default. Reader sector, issue the command. Right, so it's using motor on side 0. So let's find the read track 0 code. Yes, it's going to be reading the opposite side, which of course won't be formatted in this way. So we will change that to tell it we want to read from the other side. Okay, so that should have that for us. Okay, that's looking better, because it should be nothing at the beginning. Oh, look at that! We're seeing what we want to see here. Hi Maurice, welcome along. Okay, so what we're trying to do now is to do the decoding of the track information block. So we're getting the data field 65, and then we're decoding some bytes out of that, which is all well and good. Cool, so let me implement something to decode that. So I'm going to just reduce some of the spammy output from this for the time being. She'll make that conditional if show gaps. Int show gaps, so it's easier to get to and find. So you put it right up the top, so we can have the verbosity display options up there. Right, so now it's much more abbreviated output. So this is the lead-in gap bytes while we wait for the head to be guaranteed to switch to write mode, because that actually takes a little while. We then get our 3 sync marks. That's great. We get the 65. So this is the track information block marker. And then we have some information about the track. Now, even though it's been written to track 0, the histogram tool just always pretends you're writing to track 40. So let's have a look at this is how we write the track information blocks. We write the track number, we write the data rate. It's being written as 28 as well, which would suggest HD rather than, did we wind it back out? What did we have on that track? Yeah, it is. The TIB says 28. Yeah, because and they're all nicely spaced, right? So this is HD density of that, so that's all good. Yep. So we get the track number, the data rate, and some encoding information that will tell us whether it's MFM or RLL. This is going to change a bit because we're actually going to support an additional type of RLL fairly soon. That will let us get higher data density, I think. So describe data, here we go. Case OX65, MEGA65 track information block. Track equals percent D, divisor equals percent D, percent 0.2 F megahertz. Encoding is percent O to X. Okay, data field 1, data field 2, 40.5 divided by data field 2, that will get the megahertz, and the encoding is data field 3. And remember to put a break in so that we don't have endless entertainment. So we should right, 65, print that. Okay. So why is it they're not showing it? Because it knows we have a data field type 65. Data field type. Okay, that's... Why is it not calling describe data? 14 bytes is last sync. Ah, okay, right. So this is a funny thing with the way this decoder works. It only prints out the decodes the data area after it hits the next sync. So yes. Now, what were people saying there in the comments? There's a bit that's gone past. Whether I've missed anything that's important. It sounds like the music is going towards a climax. If this was a movie, Paul would have it sorted by the end of the song. Indeed, that would be nice. Unfortunately, it's a little bit slower going than that. So what I'm going to do is we are going to increase the data rate. Now, the reason for doing that, encoding. Is that this will mean that we get more in that capture, because we capture 64K cycles of data going past. So that's HD, and so we weren't getting enough. So we're going to bring it back to and we're not on track 0. Okay. Yeah. Let's be bold. Let's try and get data rate 17 going. Save that data. Then I need to pull that back down. Okay. Oh, and I am writing the correct track number in there these days. Okay. I think previously I wasn't, and now, since then, I've fixed it. Maybe. So that's all good. Now what's interesting is that we've just got 00 bytes coming out after. Which is most fascinating, because we know, in fact, that data is being written because we see the histogram showing the RLL pattern. When we're looking at those peaks, if we were writing all zeros, we wouldn't have that kind of distribution. So that's real data. So anyway, the first thing is we need to make it so that we decode the track information block sooner, so that we can go through. Maurice is saying, renormalizing, is that even a word? I thought normalizing is correct, but I'm not a native English speaker, so I think you can say renormalizing. It just means that you're normalizing again. So we had already kind of normalized the data for the expected data rate, and then we actually calibrate against the real data rate that we're really seeing from the floppy drive. So we are renormalizing or resynchronizing the data is probably also just as fine to say. Okay, so I need to make this switch to having the decode immediately. So after we've got 6 bytes, and the first, well, actually it's 7, right? Because the data field type doesn't count. So data, yes, so it's describe data. So data field. Okay, yep, so we get blah, 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 blah. Okay, if data field 0 is equal to 0x65 and field offset is equal to 7, describe data. Yep, no, welcome Maurice. He's just said, nice, I learned something. Well, hopefully I haven't taught you bad English. Okay, so much better. So now we're seeing that the track info block is coming through. So what we can do is we can change the divisor when we see that to the indicated rate. So what's nice here, so 1.76 megahertz, for those who were remembering previously, we were looking at, so HD uses 1 megahertz, and we believe with RLL we should be able to get to 1.6 megahertz. And which would be, so that with a divisor of 40, right, gets us 1 megahertz. So we're now at a divisor of 23 instead of a divisor of 40, so we are at almost double the data rate of what a normal floppy drive doing 1.44 meg would do. So the only thing that's a little bit disappointing is we know that we can do 1.6 megahertz. Well, no, sorry, we were never quite getting the 1.6 megahertz, right? We were getting down to a divisor of about 30. No, yeah, it was 30, wasn't it? Yeah. So 40 over 30 is 1/3, is about 1.34 megahertz. So we can now get up to 1.76 megahertz by using RLL from the benefit. So I'll do the math on that in a little bit, but let's first change this up. Keith Canaan 64 saying renormalizing seems correct to this United Statesian. This isn't the first time I've heard the term. Yeah. And I think it's used in physics as well when they're trying to get rid of all those infinities in quantum stuff, which maybe speaks against it being good English. Right, so track info block. So we want to set the so rate. We're setting down here. So we need to set the rate earlier so that we can change it from in that function. So actually what we want to say is that MEGA65 floppies contain a track info block that is always written at DD data rate. When the TIB is read, the FDC floppy controller switches to the indicated rate and encoding. Right, describe data. Rate is equal to data field 2. So now we'll change the rate to that. Now this isn't going to switch to RLL encoding just yet. But what I was hoping was that it would change some of these zeros into something more interesting. We're going to have a look back at the gaps and see what they come back in at. So actually if I take that back out, what we should see is we have no. And so we should have when we don't set it, a lower number of these zeros, because they're all assumed to be each pulse is assumed to be much longer, and when we set the rate to that, each pulse will be deemed to be shorter, and so it should... no, it won't actually, because it's still counting how long the gaps are. But what we need to do is now we need to show the gaps again, and it should respond to that. So if we search for track info block, there it is. And so this is suspicious to me that it hasn't changed, because it's still showing these gaps as being quite short rather than scaled up to the correct one. So divisor 23, let's just... Yeah, so we're setting that there. If we don't set it, what are we seeing? Okay. They should... Because this really should be changing how they're looking. Hey, Deathy, welcome along as well. Maurice MEGA65 saying, the graphs that you showed earlier, what do they indicate, especially the yellow-red spikes? Okay. So if we hop back over to there, this is the ones that you're talking about, right? So this is a histogram of how long the gaps are between the magnetic inversions on the floppy. So the color code is just for the ones that are above a certain threshold, so that I can kind of see where the center of the peaks tend to be. But really, that's just a reflection on the thing. And so you actually see that the longest peak is red as well. So we can see again if I need. Oh, no, I haven't got the thing set up so I can point out. You can kind of see that the very tallest one is red. So yeah. Yeah, someone was just asking something on Discord. Someone. Right. Yes, the stream is now. And James saying, "Oh, I've totally made a fool of myself in Bitstream. There's a baby lizard in my house," and I was thinking about the baby lizard while I was really nervous in Bitstream, and I'm meant to say that I typed from the small screen, and look what I typed. Yes, I'm typing from this baby lizard. That sounds very. Oh goodness me, James, the comedian that does the trolling of the scammers. And yes, baby lizards are cool. We get geckos around here. We also get blue tongue lizards here where we live. We've still got enough bushland around our house here in Adelaide, in the city. So yeah, no. So Marisa, the red is not an issue. That's just, it's a good thing. It's showing us where the tallest peak is. So yeah, that's all good and fine. Okay, so let's try and figure out what the flibbits is going on here. I want to know what the show gaps. That's fascinating. So what I'm trying to do here, so it's dividing by divisor, not by gap, but by rate rather. Because we set the rate once at the beginning, and that's that. Because okay, we have a real divisor, and we actually have the actual divisor in the code is adjusted based on the sampling rate, which is every 3 clock cycles. We'll just calculate it every time. So now we should see it respond. Yeah, so now they've gone and got bigger. And that's a good, oh no, it's just a single sync on its own. Track info block. Actually, we need to fix that decoder. Data, oops, track info block. If field offset is greater than 6, because otherwise we're decoding it multiple times even though we haven't actually got new stuff in there. Ooh. So then there's another sync mark. Okay. So I think we're on the way here. The trick now is that we need to have an RLL decoder instead of the MFM decoder activated, because the encoding is indicating that it should be RLL. So let's have a look, because I thought it was bit 7, but apparently it's not. Oh no, that's gaps, no gaps. Bit 7 is... I'm not even writing the encoding, whether it's RLL or MFM in there. That's a stupid on my part, isn't it? So we'll have to fix that. So I'll just make the code here pretend that we're switching to whenever we see one. LGB says, I'm totally lost in the lizard topic already. Lizard of war? Indeed. So you know that here in Australia, until only 5,000 years ago, we had... Oh, can I remember the name of the blasted thing? It was a goanna. So we still have goannas, but our goannas now are only about a metre long at most. Megalania, I reckon, is the name of the thing. So, not technically a dinosaur, but oh, hang on, it's stupid. I hate the way that Google, when you find a search link and you click, you want to just copy the link, you have to actually go to the page first. Otherwise, you get this complete rubbish link. So it's a lizard rather than a dinosaur. But this thing was mean. So it was up to 5 meters long and basically just ate whatever it wanted to. Yes, very scary. And so Aboriginal people were around in Australia when this blasted thing was around. I was trying to find when it went extinct, but can't find it. But back to the task at hand. Right, so here's our quantized gap for MFM. So I'm going to call it MFM. Then we have quantized gap RLL27, because it's the RLL27 code that we're looking at. You're welcome there, James. It's all good. So now we have gaps between 2 and 7 is the convention to describe them. But what in MFM we call a gap of 1, we actually call a gap of 2 in RLL. So it's actually why we had that. Remember we had that factor of 2/3 when we did the divisor, and that's because we want to halve the number to use the MFM kind of thing. So we can actually, let's just go float divisor. If not RLL encoding, divisor is equal to that, else divisor is equal to rate on 3. And then we have the quantize gap MFM and RLL. Right, so if the gap, so that will now be double that. So, well, realistically, if the gap is less than 2.25, we will call it a 2. Else, if gap is less than 3.25, we'll call it a, well, actually less than, we can make these broader. Two, 3, 4, 5, 6, 7. Well, in actual fact, if the gap is longer, we just call it 7, right? Float quantize gap, float gap. If RLL encoding, return quantize gap RLL gap, else return quantize gap MFM. So basically pick which method we need to use. And oh yes, and I haven't defined RLL encoding. Int RLL encoding is equal to 0. Okay. Oh yes, because it's RLL27, not RLL. Okay, so we hit the track info block, and now we're getting gaps of various sizes, and that's all good. And so now the next trick that we have to deal with is that the sync marker for RLL is different. So now someone was busy asking questions. Right, yes, Maurice comments on the Megalania, not something to mess with. No! And Tron602 says, aren't MEGA65 pools also dangerous Australian creatures? Everything's dangerous there. Yes. So, should be nice to me then. LGB, this is Australia style, I guess. Is this a knife? This is a knife. The pool version is this a HD floppy with a 1.44 meg capacity? No, this is a HD floppy with 3 to 4 meg capacity. Exactly. Very Paul Hogan. And James says, people think I made a syntax error ready, but of course we all know that I didn't subconsciously mention lizards because I'm excited about the lizards in my house and subconsciously excited about the MEGA65, and my Freudian brain got confused. No, we'll definitely not accuse you of that one. And 602 says you can, Tron602 says you can omit the last else unless you're adding other methods later. Correct. And we will add other methods later, but we're not worried about that just yet. Now, the sync marker for RLL gaps to bits is, it's a 7 followed by a 2 followed by anything else. So it's a simpler sequence, but of course because it's a 7 and 2, that's longer than in for MFM. So 2.0, okay, here we go. So this is sync gaps MFM, sync gaps RLL 2.7. Sync gaps. Okay. If not RLL encoding, else. So this is for RLL. Copy paste. We only have to look at 2. And so we just do a bit of magic here. If I is equal to 2, I is equal to 4. So that the follow-on code works. So we should then see a sync pulse, and we're not, but we're definitely seeing things that look like they might be data, which is all a bit interesting. So let's come back down to the track header. So I wonder if we're dividing by the wrong things. I think we're now getting closer to where the issue will have to be to decode these. So let's have a look at what we actually write when we're formatting a disk. Right, so we have written out our thing, and now we go back to 598, which should be the end. So we should have some 4E bytes in RLL encoding. Now the first 2 or 3 are going to be mashed up because we actually have to allow time for the encoder to write out the last bytes that were in the buffer in RLL encoding. So if we actually come back down here, you can see we actually restore the encoding. So we write out 4 bytes of 0 to make sure that that happens, and then we switch, and then we should start getting, we should get 2 bytes of 4E, and then 4E because it's 598, 599, and then we come back up here and start writing out the next sector. So we'll start getting sync marks again. So that's what we should be seeing. Probably the next thing which we need to do is to make our RLL decoder. So there's our MFM decode, which I'm probably just going to use for both of them, because we've got, yeah, so this is the MFM decoder, so we're still decoding in MFM, right? If RLL encoding RLL decode bit, or decode gap is actually what we want. Else no, MFM. Let's call it RLL27. We call it RLL27 decode gap. So now the funny thing with RLL decoding is that it's a variable length code, which makes our life a little bit interesting. So we need to have the table for that, which I will scab from somewhere in a second. In fact, I have it. Here. And let me go back to there and get Twitch back up. Okay, so now the other trick that we actually have is that after that 7 and 2 gap in the sync mark for RLL27, we actually have to skip 3 bits. So there's a sync mark. So if RLL encoding skip bits equals 3. Int skip bits 0. So now whenever we get a gap, we need to append this to our existing buffered bits. Unsigned jar buffered bits. We should never need more than 16 from memory. We'll worry about that if we need to. Buffered bit count 0. Okay. So if we have a gap of some length, so if we have a gap of 2, which is the shortest gap that you can get in RLL, that means 2 zeros followed by a 1. So what we want to do for int I is equal to 0, I is less than gap, I plus plus. Buffer bit 0, buffer bit 1, if buffered bit count less than 16, buffered bits, buffered bit count bit. Okay. But remembering, if skip bits minus minus return. So that will skip those first few bits. So then what we want to do is to look at those first few bits that are in the buffer and see if it matches any of these strings. So if buffered bit count is greater than or equal to 8, we can look for those longest ones. You should always look for the longest matches first. This is part of how the RLL decoder works. So we should have some... Do you know what I should do? I should... And now we can do a string comparison. And I need to sneeze. It's not going to happen yet. If not string comp 1 2 3 4 100 comma buffered bits comma 8 emit bit 0 emit bit 0 through copy So we're chopping the bits off, right? And this will just make it easier to edit them after. We'll do else if for safety, and so the next one was 001. So it's that, and it encodes that. So now we can get our chart where I can see it there. We can do these three. So we've got 100, 100 gets 0, 0, 0. What was the next one? That's we drop that leading one to a 0, and then that gives us 010. And the last one is 011, and that gets us that. Okay, so now we do the two 2-bit codes. Four. 0100 gets us 10. Right, so in theory that should work. Because I've used string copy instead of string copy. I think string copy can do overlapping strings. That'll be the only other complication if I've bollocks that up. I still have an error, right? Oh, yeah, it's complaining bitterly because oh yeah, I'm still using strucump there. Oh, that should be strucump as well. And we should just make that char instead of unsigned, and that will quieten lots of that down. Okay, let's oh, there's no student copy. There is student copy. We're probably not including string.h. No, that would be why. Okay, that's better. Line 212. Yep, a semicolon after return will indeed be helpful. So we're still not seeing anything much there, I think. Rather, we're seeing rubbish still. We know that they must be getting written correctly because the peaks on the histogram are nice and clean and evenly spaced, and all the rest of it. So, yes, it's a bit curious. Where's my cursor gone? Someone's asking a question about where to find the SID mixer coefficients. So I've just answered that now. Okay, take care, Marauder, and we'll catch you around. It's just saying he's got to head off. So let's have a look at. We know that we're going to have some 0 bytes, right? And we're going to have some 4E bytes. So let's see what 4E should encode as, right? So that would be 4. Okay, sorry, we need to look on here, right? 4. So that will be 010. So we should see that So dollars for E is equal to whatever comes in ahead. So 010, so 00100. And then we need 2 zeros and 2 ones. 1, 2, 3, 4, 1, 1, 2, 3. And then we need 1, 0, 0, 1, 0, 0. So if we mush that together, again, so one of the annoying things with RLL is the preceding bytes actually make a difference on what comes next. So we're going to have at least 3 zeros on the front, possibly more. And then we're going to have a gap length of 6. So there's 6 zeros in that sequence. And then there is a gap length of 4. So we should be expecting to see 6 and 4, and then the follow-on we should see a 5, right? Because we'll have the 2 zeros there, and then when we come back to do the next 4E, we should get 3 more. And so we know that we're going to have the zeros first. So the zeros, interestingly, should be writing out this 100 pattern repeatedly, like this. So I wonder if it's not that we're dividing by the wrong thing, because they should all be gaps of 2, not gaps of 3, except that, you know what I reckon it is? That our gap thing, we're actually counting the total time between pulses. So the gap, so in RLL they talk about the gap length, not the total interval. So if we do the RLL quantize gap RLL, we actually need to subtract 1 from it. Right, so now we're getting 0 bytes, and we're seeing a sync and a sync and a sync. We are seeing RLL sync bytes. This is very encouraging. And then we're getting a data field type of 0. So what else are we getting in there? 009, and then rubbish, and it's getting lost. But that's still progress. I'm actually just going to commit this as well before we get any further. Git commit source tests floppy test work on decoding TIB and RLL decoding. Right, show gaps. So we're only quantize. Yes, if show quantized gaps, so we're instead going to have a look at what the quantized gaps come out as. Right, let's get our track info block. Is our sync mark. We can can actually see here. So this is our sync mark, the 722, 722, 722. And then the next byte is from all of this. So actually, so first up, I think I'm going to go back to RLL 27 gaps to bits, because we're quantizing. Just want to make sure that I'm not stuffing up in the VHDL this same thing as to why the sector headers are not showing up. But as you know, I'm getting ahead of myself. We need to make sure that we can decode it in software from this capture before we worry about anything further, or at least understand what's going wrong. Because what are we seeing? So we're seeing a gap of 3. So we know that the 722 will actually be the sync mark. So the data will be the 3342 onwards. So what we want is to think about what that's. So we're getting 3, 3. This is the data that's coming through, right? So if we try and match that, that will get us 010, which matches to there. Then we've got 0100, so that will get us to there, and then we've got 001, 001, so that's the start of that. So the byte that should be getting decoded then should be 52. What was it? I think we're going to have a look at the accumulated RLL bits to see, because I reckon it might have something screwed up with the buffering of that. When we detect the sync marks, right, we should actually flush the buffered bits. Let's have a look at what's in here. What have I stuffed up now? Oh yeah. Writing dribble in the file to see what's going on. Okay, so we can see the bits being stuffed in there. That's all fine and good. except that that's... Ah, okay. Oh, because I'm putting it stood error, so it's not getting stood out. So it gets properly interleaved. Okay, so we find the track info block, and then we're stuffing our bits in. That's all good. So we're finding sync marks, and as we're finding the sync marks, we're still accumulating trollop onto the end. When in fact we need to flush the bit buffer when this happens. I think is part of it, right? We shouldn't keep accumulating bits every time we see a sync. So let's bit buffer 0 is equal to 0, bit buffer count it's bits buffered, isn't it? Nope. Buffered bit count and buffered bits, right. Okay, right. So we should, right, so we're seeing a sync mark, that's all good. So we've dropped the trailing 3 bits. Now what's going on? Because we're expecting, what did we say that we're expecting to see? 3, 4, 2. Yeah, okay, so I think we don't need to skip bits because we are chewing up the bits that the sync byte has left. So I think I'm still doing something wrong with that. Because of course we detect the sync after we've put the last gap on. So we actually just need, we don't need to skip 3 bits, we need to pop 3 bits off the front. And the trouble is we don't know how many bits were already in the blaster buffer. So let's, so it must be doing this in the hardware a slightly different way. So I think we can say we don't need to skip bits and we should get something closer. Three, 4, 2, which was what we said we were expecting to get, wasn't it? Oh, it was 3, 3, 4, 2. Okay. But the other thing that's got me surprised here is that we are throwing away the buffer without omitting anything. Buffered bit count. Let's buffered bit count. Keep an eye on that. Yeah, so we are dropping that into, okay, we are emitting bytes eventually. One. How does that match against the... Because it's possible that we can actually have bit sequences that don't match against any valid code. But I don't think that's what's happening here. So the 4E bytes, so we're expecting a gap of 645. Let's just have a look back and see what we were... Well, no, we're past that actually, so we should see the sync marks, and then we should be seeing an FE or an FB, because we're now in RLL encoding with the sync marks, and so we should get the sector header marker next, which I think from memory is an FB. Sector header sync marks. Yep. No, hang on. The data block is FB, so it's FE for the sector header. So an FE is going to look like... Now this is assuming that it starts in phase, right? Because again, it could look different. So and then E is going to be 01, 100. So it could look like that. Or if there was already a bit consumed at the front. Except there shouldn't be. It should start properly lined up because we have the sync in there. So we should see 3, 3, 3. Sorry, 3, 3, 4, and something. 3, 3, 4. Cool. So it's just our decoder code here is stuffing up. So we should be seeing the one at the end. God, I have to get my head around exactly what's going on here, right? So when we find the sync, we've got a gap of a 7 and a gap of 2. And at that point, we say, right, we have a sync. So this is the gap of 2 here. And then the 1 has already been emitted. And we actually write a gap of 3 when we're writing the sync mark, I think. Let me have a look again. Bits to gaps sync. So we write it like that. So we write a gap of 7, a gap of 2, and a gap of 2. So indeed, there's our gap of 2, and there's our next gap of 2. So there should be a 1 written out when we discover the sync. Still, I think this is what we've now got wrong. Buffered bits 1, 1. Okay, let's try that. Right, 3, 4, 2, 2, I think is what we said we would expect. Oops. 3, 3, 4, 2. Yep. Okay. So it's a little bit funny here, right? So when we stuff that in, there's now enough bits it should be able to decode the first part of that. Because the 1000 typo. Okay. That would quite likely cause the problem. Three. Except 2, 2. So if we're writing out FE, we should have had we're expecting 3 and then 3 and then 4 and then 2. Which we have 3, 3, 4, 2. So we're still stuffing up something with the when we digest the sync mark, we're not leaving enough of the bit sequence in there. So let's have a look at how we're doing that sync detection again. Right. Sync gaps RLL 27. So if they match, then we break. Right, okay. Yes, because we've already chewed up 2. So we actually have to check the last 2 gaps that have come in. Otherwise we are naughtily eating up gaps that we need. Okay, and so now after we've got the sync, 3, 3, 4. And so now we do need the skip bits to trim those 3 off the front. So skip bits. Well, except, so what we want to do so you want to keep the leading 1. Don't we? Yes, we do need to keep the leading 1. So we do just need to have skip bits equal to 3. So there's a corner case here that I'm not going to handle properly, because we're physically putting a 1 in after we've read the sync pulse to kind of patch things up. So that's the 1 that we are putting in, and then this is our 3 bits that we want to skip. So it's going to work on this occasion if we do it, but I'm not convinced it's going to work otherwise. Now, actually, it doesn't matter, because always after a sync byte we'll have an FE or an FB. So for the purposes of our decoder testing, it will actually be fine. Skip bits is equal to 3. And now we have 1, yep, so 3, 3, 4. Yeah, see, it should have popped off the bits at that point. Where's our emit bit so that we can enable some debugging in that? If RLL encoding, show the bits as well. Okay, so here comes bits. We get the 1 1, the 1 1, and then indeed it's this next one is not matching. Now it should match because the prefix is correct. We're doing a strncomp, and we're allowing it for it to be more than 4. Whoops. What did I just press? Right. So I just want to see that it's actually able to get to that point at that point. Yeah, see, it doesn't. So when we decode the gap, so we add the gap, right, okay, yes. So here's the rub. If it's 8 or more long, we do that. If it's 6 or more long, we do that. And if it's 4 or more long, we do that. But this only happens if it wasn't longer than 6 before. So we need to check those others first, but we still need to allow the shorter ones to be checked. So we actually can just do if, because we're trimming off the other bits first, we should be fine to do that. Data byte FF. Okay, so here we've got a problem with the decoder again, because when we've chopped off this one, we should have still kept that 0 at the front. We don't seem to be doing that. someone asking a question about EC compliance for the MEGA65, so we're trying to make sure we saw all of these things. Okay, so if we omit those bits, so there's our 1 1 1 1 1 1. Yep, that's all good. But we are then trimming too much off the front. So when we do that, so I reckon it's these certain copy things are probably the problem. Bit buffer shuffle for, let's have a simpler formulation. Actually, oh, this is what we want to do. That's even easier to read, right? And then I'll make sure that we have overlapping string safe version in there. Hey Heinz, welcome along and good morning to you too. I'm not sure whether it's quite morning for you. It's definitely still morning here. Yeah, in some sense this one is, I freely admit, a little bit less exciting as we try and grind through debugging rather than making great headway. But hopefully we'll soon get on top of whatever this problem is. So now we make that shuffle routine. So we'll do a safe shuffle down here. Bit buffered bits I is equal to buffered bits I plus n. I think that should be good. Yeah, mind what I was saying. Still good to see MEGA65 content. It's all important. Yep. Yeah, certain copy is not overlap safe. Leiden23 is saying, is it? And I think you're quite right. That it's not, which is what I've just had to deal with. Haha! Look at that! Data field type FE. And we're now getting some useful bits. And there's our 4E sync bytes. Okay, I'm just going to turn down the output now that it's closer to working. Okay, look at that. Progress. And a good explanation as to what has gone wrong. We've got a CRC fail in the sector header. And we don't have quite enough data to get the whole data track. But you know, a good thing with this, right? So this is recorded with rate 17. Hex, so 23 decimal, 1.76 megahertz, and we have correctly resolved those things, so that's actually really encouraging. So let me just git commit source tools, more work on TIB RLL decoding. So this is, I'm getting more excited now. So the question is, how have I stuffed up the CRC? Because we have our sector header here. I'm just going to put a new line on the front of that, just because it sucks having to find these things in the middle of the goop. Because all of that looks correct, so it's clearly that we've just got the CRC wrong. So let me just go. So the fun bit then when you have a CRC file like this where it's being written incorrectly is to try and figure out how it's being done incorrectly. I'm wondering if we're not now hitting some funny problem where the CRC requires more cycles to calculate than what this data rate allows time for. But that it doesn't make a huge amount of sense to me that would be the case. Have a little bit of a think. So the CRC has an interesting property, right? That when you calculate it, including the 2 CRC bytes, you get 0. So it's really easy to test when you're reading, and you have a bit more work when you're doing the writing, but not a great deal more. So the trick will be to work out what the expected CRC is, which I do for the data field one, right? Yeah, that's right. So you have to pull out the calculated CRC 2 ticks early. So 6 will be the last one. So if at 4, just move that calc CRC up so that it serves both. And we've got two bytes there that we need to get. So it's data field 5, data field 6. Whoops. What am I doing here? No, yeah, I need to cancel that. Down there. Right. So let's see what it says here. So it should now tell us what it saw and what it expected. So we can try a bit of brute force to try and figure out exactly what is going on. What we can also probably do, in fact, is under simulation, we can run the VHDL and get some information on what bytes it's feeding into the CRC as it goes through. And watch what happens there. I'm just going to duck off for a moment or two. I will be back in about 2 minutes. Feel free to be hypnotized by histograms in the meantime, and we'll see you back in a second. Okay, back again. Just a glass of water and a bit of food, feeling a little bit low blood sugar, but all is good. What's, why do I put that's something funny in there? Is that the problem? No, because that's the checksum. So the O2 is the sector size. Just want to have a look at the code that's printing that out, right? Because it yes, that will help. This won't fix the CRC. But it's just calculating the expected sector size from the sorry, what have I missed? 4 1 2 3 4 5 1 2 yes, right, okay. That's what the problem there is. Yeah, so the sector size field is 2, which means 512 byte sectors. Okay, so what did we decide? That we needed to figure out why the CRC is wrong. And then we have got something else going wrong here, but we'll worry about that when we get to it. So this is actually the sector data being written out, right? So it should count up monotonically, but we're seeing that it's going to gibberish after a while. So maybe 1.7 is a little bit too aggressive. Or just we've got some other bug in the decoder at certain bit combinations, which is also entirely plausible. I guess which we need to make sure isn't causing us to misread. No, it can't be causing us to misread the CRC because we're still in sync. We're getting the 4E gap bytes after, which is all good and fine. Okay, so let's have a look at the simulation then. What am I doing here? Oh, that's right, because we haven't got that directory there. Okay. So we have a simulation target that has just the floppy controller and simulates as if the CPU were telling it to format a disk. And so we can set the data rate in that, and we can tell it RLL, and it should write out exactly the kind of disk that we're seeing here. So that's, I think it's test MFM. Somewhat confusingly, I have test MFM and MFM test, which are two quite different ones. Okay, set the data rate to so 17 hex, which is 23. And then we're telling it RLL encoding. Now to check, because I've changed the meanings of the bits in here. D6AE. So now the encoding is in the bottom 4 bits. We tell it a 1. With right precompensation, sector gaps. Yep, that's all fine. And then we tell it to start formatting. And what we should see, so this B2B is bits to bytes, so this is reading bits in, so it's reading the MFM bits, and we should eventually see, I think, yeah, track info. So it's formatting and then it's reading back what's being written. So we should see the track. So it's track 1, still rate 17, encoding 40. Sector count 0, CRC AE E2. Okay, so the CRC is fine on that. But what we need to do is, remember we had that issue where I said that the track information block wasn't writing out the encoding. So what we want to do is 7 down to 4. In the top half, we are putting the encoding. And then what we're putting in the bottom half is the encoding. Now it's in this saved thing because when we're writing the track information block, we actually temporarily are replacing it with MFM and the low data rate, right? So yeah. What else are people saying here? Leiden 23, in response to questions about whether there's life outside of bits and bytes, has decided to start relearning Japanese and enrolled in an online course. Excellent. It's good to learn another language. It's good for the brain and all sorts of things. Leiden 23 says you need to do something to distract yourself from the wait for the pre-order start. Indeed. And James Anders Bank saying, how's it morning? If you're telling me that I have to get up and do stuff, I'm going to thump you. It's 23 past midnight. Yes. Quite so. Okay, so we're going to encode that. Now test MFM. I'm just going to add in, because it was on track 1. I want to put it to track 0. The reason I want to do that is I want to make it exactly like what we have on our track that we've read, so that it's byte identical. 1, 2, 3. Right, so here we test, set the data rate to 23, D08 4 go. tell it to write to track 0. Track number is 0. That's right. Now we have the sector count in there as well that I'm putting in, which wasn't in there before. So this is going to mess things up a little bit. DO84 is a track number. Actually, that's from DO85. Right. That's all right. Because the sector header will still be the same. Because yes, since that bitstream that I was using, sorry, what was it? DO8 5 is the sector. Yeah. So I've now made it so that when you set the sector count to some arbitrary number, 42 sectors per track. That's what the in the track information block will actually be written as a number of sectors per track, which is, it just makes it a little bit easier for things that are reading it. Okay, so just hang on a second. My son wants to ask me something, I think. Right, that's right. I had the headset on backwards before. Okay, so that's all going to get written in there, and then we need to tell the, when we see a track information block, it's in the MFM decoder, I think. Yes, that's right. So we do the track info, and we've now changed this so that we have track number, data rate, encoding, sector count. Right, okay. I've already got that in there. Yep. So we should get a report on all of that stuff in there, which is good. And we know that that was working before because the CRC is valid. Okay, track info encoding. Track info valid. Right, so if we get a valid encoding, what I'm trying to find is RLL encoding. Oops, RLL 27 encoding. We just need to set the encoding format. So it's FDC encoding mode. Track info valid. FDC track encode. So it was FDC encoding mode, wasn't it? FDC track info encoding 3 down to 0. Report track info setting encoding to info block. So that should automatically set it to RLL. Now there's a thing that we need to do here with this, which is actually we need a flag to say whether we want to honor the TIB info. So if use TIB info, so we always record the info, but it's a question of whether we want to set the encoding and everything automatically on it. Signal use TIB info stood logic on. And so this is important because when you want to format a disk, for example, we want to use the correct information. And if you're trying to do a high density disk, you want to be able to change that. What's interesting is if this flag is set and you try and format a track, it'll try and format the track using the same parameters as before, which is actually probably a sensible thing. So I reckon we've got a spare bit up here in D6AE that used to be used for other things. 7 SD TIB enable. Enable use of track info block settings. Use TIB info fast IO work data. 7. Right. And we need to make it so we can read it as well. Fast IO data. 7. Select RLL encoding, enable TIB to set data rate and encoding. Okay, let's try that. Duplicate choice for 5, okay. Well, indeed it is. Easily fixed. String blah 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 blah. Okay, line 56. What? Test. Oh, 174. Sorry. Yeah, okay, because I'm not okay. It's D3084 because this is using the internal 28-bit addressing of the MEGA65 for those register rights. Whoops, sorry. 3695. Set only the high nibble because we're only providing 4 bits. Okay, let's try that again. Okay, so it saw the block marker. It sees that it's track. Why are we still getting track 1 written in there? Because we've written 0 into the track number. We'll revisit that in a moment. Encoding is 40, saw sector count of 0. That maybe those writes I'm doing aren't working. Okay, so saw track, set encoding to 0 from track. Except, did we set the encoding to that? Apparently we have. So an encoding of 40. Yeah, we're writing. Oh, hang on. Let's see what we're actually writing to D6AE. Well, actually, we said we're writing F0, but we're actually writing F1. Report D6AE writing dollars. Just want to see what's actually happening with that. Yeah, so it is getting written. Ah, except duh. Right. We've made it so you can read the encoding using that register, but not write it. So this could be causing all manner of hilarious problems. So we allow setting it there. Just wondering whether there was any other path that I'd created to allow it to be set. No, so I'm not sure how we were even, in all honesty, formatting the... Oh, this is because it's before, that bitstream that we were testing with before, was using the old method of doing it. I took the debug out of that, didn't I? Yeah, I did. So let's see that it's sort track 1, rate 17, encoding 41. Okay, that's better. So it's being set. So now that we've just got this mystery that the track number is still wrong. MFM. Oh, it is in here, isn't it? So it's X65. So we write the track number, F011 track. Which is from D084. Pretty sure. Yep, D084 is the track number. D084 is the track number. Report D084 setting F track to and it's not being written, so I've clearly stuffed something up with that address formulation in here. Because it should be that. Let me just, on the real MEGA65. D3084 to 1. So that's got that there, M777 D084. Yeah, that looks like that should be. Ah, you know, what I suspect it probably is. Remember, this is not running with a full CPU. So I've probably not implemented the, yeah, so we've got SD card IOCS. What we actually need to do is, it's a different CS line. F011 CS. Same with this one. So this is just purely for my test harness, right? SD card IO CS is equal to 0, F011 CS is equal to 0. So we just set the appropriate CS lines based on... Oh yes, okay, I was doing it like that. Right, okay, we'll still do it that way then. So rather than sitting at the top, I was just changing the signals as we go through. So we need to clear SD card IOCS so that we don't write to goodness knows what in the meantime. Okay. Let's see where it's up to now. Okay, saw track 0, excellent. Rate 17, yep. Encoding 41, sector count 2A, that's the 42 that I just put in as an arbitrary thing, right? And then we've got our CRC. Right, so at that point we're all good. Now what we need to do is going to, because we've got a few little fixes there that are actually quite helpful for us. Fix various bugs with TIB RLL encoding. So now what we care about is whether we are now able to work with it. Hang on a second. Okay, so let's actually hang on, it's SD card IO. Nope, so it is an MFM decoder. Report. Still put on the track info label. Post sync byte equals so this will show us the 65 when it finds it. Yep, so we see the post sync byte is 65. So what we should see is a little bit further down. Track info. Oh, okay. Why are we printing that out all the time? Just MFM line 208. Okay, that's just, we don't need to display that all the time anymore. It's just showing that the track info rate has taken effect.
It's impervious to all poisons. If it's blown up, its cells will regenerate
Right, so we're seeing the encoding is being set. That's fantastic. Post sync byte FE. Cool, so it's seeing the data byte. This is good. So we're in the right spot. We want to see what data bytes are being fed into the CRC. No, that's the wrong CRC. Okay, let's is our track info. So one thing that's worth us noting here again, my theory that the CRC may not be fast enough, is that it does take a number of cycles to calculate the CRC byte. So what I'm looking for now is where it's writing the sector header. I want to see what it's putting into the CRC. So there's our A1 byte. So what should be in there is the 3 sync bytes should be counted in there. And then we should have the FE, and then we should have the various bytes of that. So we have the A1, that's all well and good. We have the next A1. We have the next A1. So it's also showing us what the cumulative CRC value here is, right? Which is good. Then we're feeding it with an FE, so that's good. Then we're feeding it. Feeding it with a 0. And then for reset asserted. Now, what might be happening here is that there are probably 2 CRC generators for MFM and for RLL encoding. So the fact that it's resetting here might be actually a furphy, but on the other hand it may not be. So ideally what we need to do is we need to put an identifier in the CRC, generic ID integer 0. Okay. Because then what we can do is this. If I copy and paste that, we can basically have it so that we can tell which CRC we're talking about. I can never remember whether we need to put a semicolon there after the generic map or not. People have been commenting about how much we think we'll get. Hi Sammy. Just make sure we get back up to where people were up to. Okay. Acmafin says, hello, almost forgot it's Friday night. Yep. Hi Anton, welcome along as well. Acmafin's asking, are we still using MFM? No, we're doing indeed RLL 2,7 at the moment, trying to debug what's going wrong with that, with the CRC calculation is the issue. And it's looking actually quite promising as to what we'll get. Acmafin's saying 42 sectors per track, where did you get that number? Precisely, it's just it's a natural number. It's not actually representative of how many we're actually getting, it was just, I needed a number for there. And Sammy's asking how far, okay, start putting bets on how much will actually fit. Acmafin says go with 4 megabytes. Anton's betting 3.6. Sammy's asking what the stakes are. Acmafin says I might be over optimistic, but I hope I'm not wrong. Sammy's saying I'm going 5 meg. Oh, that's a pretty bold bet. Leiden 23 is saying 3.8. So let's actually do a quick calculation on where we're currently up to. So we were saying that we can get, we're having a rate of 17 hex, right? Which is 23. So a standard high density disk uses 40. Now we know we can't do the 23 rate over the entire disk. So it will be less than this, unless I come up with other ways to improve it. So why is that coming down at only? Oh yes, right. So this is, if we have sector gaps, it will be about 2.5 meg, and without it should be 2.75 maybe. I think I must be calculating something a bit funny there, because there it's sounding a bit low compared to, we know that we've already managed to get about 2.6 meg with MFM with track at once. So if we multiply that by 1.2, we get over the 3 meg barrier. And that 1.2 is coming from the old maximum data rate we could get divided by the new maximum data rate, which is actually now 1.3 in fact, because before we weren't sure we could get quite that high. So that's already potentially up around 3.3 meg, which is pretty cool. And that's without write pre-compensation. That's without shifting that, that one peak that we know walks to the left, and that we might well be able to come up with a way to do that. So back to the debugging. So I've put ID 1 on there, so that should let us see. I'm just going to improve that a bit more, in fact. So we have we keep saying when reset has been asserted, right? And last CRC reset is equal to 0. Last CRC reset. So we just want to get told when the edge changes, right? When the value changes, rather. Signal last CRC reset. Yeah, we don't need that one because we're already displaying it elsewhere. Right. Okay, so now we can hop through much more efficiently. This makes me much happier. And what are folks being saying a bit more stuff here. Where are we? Deathy says, Sammy, I'm so invested in how much we can fit in a disk that I wouldn't want to jinx it by betting on it. Sammy saying, I know, meanwhile I going right out there. Deathy, hang on. Acmafin saying, yeah, if you bet $1 million for 4 megabytes and then he reached 5 megabytes, so you don't win with your luck. Yeah. Deathy says, if I had $1 million to bet, then that would still be worth it. Excited about how much we'll be able to fit in the disk before we go to multi-discs. Acmafin, other than maybe he could reach that by buying top-notch hardware. Yeah, that's right. I do have an extended density drive here, which in theory would let us get higher data rates again on 1.44 meg floppies. And Death is saying a huge multi-disc game is rarely going to be more than 2 or 3 discs. Yeah, I think if we get this right, that's totally possible. And Sammy's saying, if you've increased the linear density, how much can you increase the track density? Unfortunately, not at all. 3.5-inch floppies don't let you do half tracks or any other kind of fractional tracks, which is very sad. Okay, so back to here. So we can see that we're getting fed the first sync byte. There's our bits. We get fed the second sync byte, third sync byte. There's our 65. So this is on the previous one, right? Yeah, Aquafin, I completely agree. It's a stupid design, but it uses less lines on the interface, and I think they tried to make the 3.5-inch drive smart. Would be interesting to see if we could do terrible things by stepping backwards and forwards at the right speed, so that if we know how fast the head can move and we know where it was, to try and get it to go halfway between tracks. But that may not be good for the lifespan of the floppy drive. Well, correction, I think it won't be good for the lifespan of the floppy drive. It will make the stepper motor very sad and probably very hot. Okay, so we're resetting the CRC again. We're feeding in an A1, that's good. We're feeding in another A1, that's good. We're feeding in an FE, that's good. We're feeding in a 0, yep. We're feeding in a 2, yep. And is that the last? See, I reckon that's left a byte off the end, hasn't it? So that's saying that the CRC value should be 0306. Oh no, that should be right. And then it should write those values. Okay, and so that the CRC 0 is the one that's decoding our track. Okay, so we reset it. We put in the A1, get 443B. We're going to have to write these down in a minute so we can actually compare what we're getting after each byte. A1, 968B. A1 again, CDB4. So, you know, something fishy there. Ready, I think. So we've reset it and fed it with the new byte at the same time. Okay, I'm going to have to chart these. Now some more questions and comments here. Where are we? Okay, so Deathy is saying, let's see, 3.3 meg approximately divided by 300 kbit. It's only getting about 11 seconds of video at relatively low quality. Sammy says, do we know the model of the floppy drive? Yes, we're using Alps floppy drives. If I lift the lid on my MEGA65, that's the wrong. Which one do we want? Right, there it is. So it's a DF354H121G. Interestingly, if it was not the G, but there's a variant that was, I think, meant for Macs, that could change the spindle speed from 300 to 360. But let's start charting. So these are the bytes that are supposed to be getting written, right? Put it down one. So this is on encode and then on decode. What I want to do is to see what the CRC value is after each of those, because I reckon there's going to be something stupid with this. So Dr. Hawkins should say, hi, I've been lurking, enjoying the stream, returning to lurk mode. No worries. Sammy says the Apple II's floppy controller stiff motor had a 4 times higher resolution than the distance between tracks. Yeah, so that's what I would have liked to have seen on 3.5 inch drives as well, but such is life. We have to work with what we've got. Okay, so there's a A1 out, A1, 65, right? So this is the track info block, which we're not worried about because we know that decodes. Okay, this is what we now care about. So, and this is on the decode side, right? So we end up with 443B after the first one. Hey, James, again. And then we end up with 968B. CDB4. Okay, let's have a look on the encode side now. And again, we'll skip over the already that's different, isn't it? 453B. 86AA. Yeah, so we apparently are feeding different things into the CRC. Well, now that's interesting as well. We feed the two A1s in only a few cycles apart, which worries me as well. That would explain why that first 453B is wrong, because it's had time to feed one bit through and then it gets marched on. Yes. So the RLL encoder buffers 2 bytes and immediately allows the next byte to be written. So that means that these bytes are getting pumped through, and there is indeed not enough time for the CRC to calculate them. So then there is this. So how much time do we have after that? Because what I'm thinking, I might just make the CRC buffer a byte. So that comes through at 681150, 682290. How many cycles is there in between? Are there enough? But we are on the trail of this bug now, which is really good. So let's stop having superimposed screen. And it will be because of the way that we're buffering in here, because in comparison to the MFM one, we can buffer more. Okay, CRC 1581. So we have byte valid. And we're letting byte valid, sorry, it was, sorry, it's CRC feed, isn't it? That's what it's called in here. If it's equal to that, then we basically are stomping over the whole calculation that's underway and aborting it. I'll have to have what's going to be the best way to do that? So we should probably just, if CRC, Sammy, Sammy's just saying that this drive allegedly supports 160 tracks. Now, I think I read that as well. I think that actually means 80 on each side, but do dive deeper in. The Alps make great drives and crap data sheets. I think you're looking at that single page data sheet, are you? Or is this a nice... So some of the drives, like some of the TAC drives, they have like 45-page data sheets, which are fantastic. Yeah, you found the same semi-useless data sheet that I found. And I believe the 160 tracks is purely 80 each side. Because the 3.5-inch interface doesn't actually have quadrature lines for the stepper. You have a direction and a step signal. So they could have done quadrature and made it so it was 2 steps or 4 steps per track, and then we would have been all happy campers and been able to fit twice as much on. But that's sadly not the case. So if CRC feed is equal to 1, then byte buffered is equal to 1, and the buffered byte is equal to CRC byte end if. Right. So if we're going to reset So what we want to do is say if byte Okay, so basically what we're doing here is waiting until it's ready and then taking the buffered byte. So now we just need to, oh, come on, what I messed up there. So we want to feed it in at that point. Okay, let's, okay, yeah, we need to declare those. Buffered byte. Okay, so this is on the encode side, right? So now we're getting 443B 968B CDB4. This is all looking very encouraging. Okay, so that was with that one. And again, we'll see the same thing, right? 968B CDB4. There's our FE, right? So now we're getting B799. Okay, so that's looking good now. So let's, I can't remember where the SD card IO, right? So we want to, where's our MFM decoder? Right, track info. So we're looking for FB. That's the FE sector header, right? Right, so we should see a header line if we have this correct now. Waiting. Yay! So we now have the CRCs correct. So that'll be an hour synthesizing, and then I'll have a Bitstream that I can test. And this is probably actually a good time for me to wind up. The family are up and about now as well. So thanks for tuning in, and hope it's been interesting. And I'll set this chugging away, and yeah, hopefully we have some good news about how much more we can cram on a disk fairly soon. Okay, take care.